Okay, so this is going to be a really short little mini lecture on magnetism, kind of introducing you to the idea of magnets and magnetism, really conceptual based, really just to kind of get you excited about kind of exploring magnetism a little bit deeper. Now, chances are you already have some intuitions about magnetism. You've experienced magnets in your life. Perhaps as a kid you played with Thomas the Train and the little train cars that had the magnets on the end and pulled each other around or pushed each other away, or even just sticking your artwork on the refrigerator or seeing that in a movie perhaps. And so we have these kind of intuitions about magnets. Maybe you recall that, you could take a magnet, not the painted side, but you could take the magnet and kind of stick it anywhere, front, back, and it would stick to a refrigerator. But when you played with maybe the magnetic trains or the Thomas the Train, some of them would stick together and other ones would push apart from each other. So why does that happen? What about magnets makes these two different behaviors show? And then, you would try to maybe stick your artwork on the refrigerator and it would work great, but then you'd go and stick it on, I don't know, the door, and that didn't work so well. Or even maybe some different metals. You thought, maybe metals are what we needed, and some metals work and some metals don't work. And so you probably did a lot of this exploration maybe as a kid. And we can actually take kind of what we learned about static electricity. So if you haven't kind of dove into those kind of introduction to static electricity lectures, go ahead and do that before you watch the rest of this one. But we can take some parallels between our ideas of static electricity and our ideas of magnetism. So let's kind of start with that static electricity part and remind ourselves about kind of how charges work, and we'll make that parallel to magnetism. So remember, we had two charges, right? We had charged particles. We had three charged states, but two charged particles, positive charges and negative charges. And we also saw that they interacted with each other. And those interactions were that the same repel and the opposites attract. Right? So likes repel, opposites attract. We know that charged particles produce electric fields. And when we had two charged particles, the electric fields, the positive charge, the field went to the negative. So positives go to negatives, right? So positive field lines go from positive to negative. All right, well, let's parallel that with magnets. So I'm gonna kind of get the swivel here, and now we're gonna talk about magnets. Okay, well, turns out magnets also have two ends, like the charges had two charges, magnets have two different ends. We call that a north end and a south, so kind of two pieces. And the interactions actually are the same, so they also interact, norths and souths interact with each other, where the likes repel and opposites attract. So norths don't like other norths, but they do awful like souths. Similar to electric fields, magnets produce magnetic fields. And we use the letter B to talk about a magnetic field. And similar to electric fields, the field lines go from north to south. Okay, so some parallels there. It turns out there's a lot of relationship between electricity and magnetism. There's also some really unique properties about magnets. So one really totally cool property is if I have a magnet, I'm just going to use what we call bar magnet. It has a north end and a south end. So unlike static electricity where we can separate those charges, with magnets, if I were to cut this magnet in half, I would end up with two pieces, and they would become magnets. And if I cut them in half again, I'd end up with 4 pieces, all as little magnets. So magnets, we cannot isolate the north and south ends. They're always both, one end being north, one end being south, one side being north, one side being south, if you want to think of it that way. Okay, so that's kind of a cool little property. This kind of leads to the idea of a cool property about field lines. So field lines go from north to south. And because they are all within itself, they're closed loops. Now, even if I have 2 interacting magnets, the field lines do interact, but they're always in closed loops. Unlike, remember when we drew field lines from a charged particle, and they could go out into infinity. So field lines are closed loops. Another cool property of magnetic fields, or excuse me, of magnets, is that the magnetism itself is a property of the material. And this is kind of probably something you experienced as a kid, like wood, that's not magnetic, but certain metals are magnetic. Iron's magnetic, for example. So whether or not an object is a magnet, a material is a magnet, is actually a property of the material itself. All right, so that's some cool things about magnets. Now, I want to talk a little bit about the properties of the magnets, just kind of to introduce you to the idea. It's not going to be something we dive into. We're going to really talk about how magnetic fields influence particles and how they can be used for our advantage. Maybe some math, that'll be fun. Just kind of to give you an idea of magnetic materials because they're kind of cool. And as we evolve and develop more uses of magnets, and we use them all the time, our credit card readers, well, not the tap and go ones anymore, but the ones you used to swipe, that had to do with magnets. Computer systems used magnets. So they're kind of really cool devices. And I just want to introduce you to a little bit of this property of magnetic materials. They're kind of cool. So if we take a material like iron, and I look here, so here's, let's imagine this is a chunk of iron. I kind of zoom into it. And it's made up of these things called domains, magnetic domains, and they're all over. I'm just going to draw a few of them. And each one of those domains has a magnetic, what we call magnetic moment. So the idea of a tiny little magnet in that domain where the moment points from north to south. So we have these little moments in all of these domains. And when the iron is not magnetized, like if you pick up a nail, an iron nail, it's not necessarily a magnet. But we can turn it into a magnet. So this iron piece has all of these domains intermixed with one another. And if I put them into an external magnetic field, so let's imagine that this is my magnetic field. Okay, that B is what we use for a magnetic field. What happens? Well, this is that idea of attraction and repulsion. So if I were to put another magnet, I'm going to use our bar magnet, so we're going to come back to this in just a minute. So here's my bar magnet. It has a north and a south. And if I bring another magnet next to this bar magnet like this, here's the north and there's the south end, what's it going to want to do? Well, we know that the norths repel the north and the south attracts the north. So this north end is going to want to align with the south, and the south end is going to want to align with the north, and the magnet is going to want to align. Okay? Similarly, these domains, when put in an external magnetic field, so time later, these domains, they're all going to line up with that magnetic field. Now this piece of iron is all aligned north to south. it's now a magnet. Some materials have these domains that the interaction between those domains are strong and the alignment happens and is maintained. Other materials, the interaction between those domains are weak and it takes an external magnet field to align those materials. But a lot of different metals have this magnetic dipole domain, and that's how some can be turned into magnets. So it's kind of that property of the magnet. We're not going to dive into that, but that's sort of an overview, glossy look, 10,000 feet view of magnetic material. Okay, so a couple more things just to introduce you to the idea of magnets, and then we're going to dive into some of the characteristics, specifically and some of the interactions that magnetic materials have with other materials like charged particles and how those electricity and magnetism are related. Okay, so I've alluded to the fact that we use the letter B for our magnetic fields. So I will remind us of that. That's all erased and get you some of those characteristics that you can note in your notes if you're taking notes or just learning on your own. So a magnetic field, we use the letter B, so we'll often write it as a B field. Okay, so the letter B is used. There is certainly a direction, so it points, like we said, from north to south. But if I'm in a space and I know the direction of that magnetic field, that's going to be important as we look at how magnetic fields influence charged particles or current or the things we're about to dive into. And then we want to know, of course, the unit of the magnetic field. And the unit of our field is a Tesla. And we use the capital letter T for that. All right. So quick little introduction to magnetism and magnets. And we're going to continue in on some more properties. So keep watching the videos as we go into our study of magnetism. Good job.